Hello guys, welcome to another tutorial. In this tutorial, we're going to discuss everything you need to know when it comes to calculating the area of influence based on a set of points using the concept of Thiessen polygons. Now, Thiessen polygons are actually generated from a set of sample points in a way that each polygon defines a specific area of influence which corresponds to each different point. Now, Thiessen polygons are also commonly known as Voronoi polygons. So, to demonstrate to you guys how you can use QGIS to calculate this area of influence, I'm actually going to use one example scenario. Over here you can see one watershed. I have a set of rainfall stations, as you can see over here. Station A, Station B, C up until Station F. So first I'm going to show you how to calculate the area of influence. Now let's say if someone wanted to calculate the rainfall pertaining to this particular watershed using all of these stations. Now you can see that there are two stations inside the watershed, this station C over here and station F over here. But that doesn't necessarily mean that the rainfall of this particular watershed can be defined only based on the rainfall data of one particular station or in this case these two stations, because there's a good chance that the actual rainfall of this part is more representative when it comes to the data of station A rather than data of station C. Now, for example, over here, it's quite evident that the rainfall of this particular part, this northern part of the watershed, can be more accurately represented if we were to sort of account the rain which was recorded in station D rather than relying on the rainfall data of station C. So that's where exactly these Thiessen polygons or these Voronoi polygons can come in handy. So first what I'm going to show is I'm going to show you how to calculate the area of influence as well as the particular weight from each of these stations. Let's say, for example, if you have a time series of rainfall data for all of these stations, you can multiply that time series accordingly based on that particular weight in order to come up with a more accurate representation of the rainfall of this particular watershed by making use of all the stations which are available over here. And in the second part of the tutorial, I'm going to make use of the same concept, but for that, I'm going to calculate for each specific watershed, what would be the contribution from each of these stations. Now, as you can see over here, I have 1, 2, 3, 4, 5, 6 different watersheds. Now, let's say if you were looking at this yellow color watershed, and its name is Sub Catchment 1 over here, you can see from this legend over here. So one would guess that there might be some contribution from station D, A, and station C if we were to assess the corresponding rainfall of this particular watershed. But then someone could also argue saying that there could be some contribution from station G as well. And similarly, we cannot completely rule out the possibility of having some sort of a contribution from this station E, F, and B either. That's why again we are going to make use of this technique of Thiessen polygons to actually accurately define the corresponding contribution from each of these stations, from which we will be able to very accurately say that 50% of the rainfall of this particular watershed can be represented from station C, 25% from station A, and 25% from station D, something like that. Well, that's just an example. So that's exactly what we are going to find out actually from this tutorial. Alright, so let's get started with the tutorial. First, I'm going to deactivate this sub catchments layer, work with this watershed boundary layer. And we actually do not really need the reverse layer, so I'm going to deactivate that layer. And to generate the Thiessen polygons, all you have to do is go to processing, and over here in the toolbox, you can either search for Thiessen. Over here you can see that under the Saga tools, you can find one tool called Thiessen polygons. And if you open over here, you can see that you can specify the set of points and the frame size, and it'll actually generate the set of Thiessen polygons for you. Or similarly, you can even type Voronoi polygons, and over here under vector geometry, you can see that we also have a tool to generate Voronoi polygons, which is basically the same thing as Thiessen polygons. Well, for this example, let's go ahead and use this Voronoi polygons tool. And right now, if I open the attributes table of these rainfall stations, you can see that we do not have much. We just have this ID column and the station name column. So now what we have to do is we have to specify the set of input points. In this case, the points are actually the rainfall stations. And we also can specify a percentage of a buffer region. Now to get started, I'm going to keep this in 0, and after we run the tool, we'll see what happens. Yeah, if I were to move these rainfall stations on top of this, you can see that it actually generated the Thiessen polygons or the Voronoi polygons, but only at the spatial extent of the stations. Now, as you can see over here, it doesn't really cover our full area of interest. In this case, the full extent of the watershed. So what I can do is, I can actually specify a buffer, let's say about 25%. And if I run the tool again, now you can see that it actually got extended beyond my study area, as you can see over here. So I will just go ahead and get rid of this first Voronoi polygon layer, which we generated. Alright, now how to interpret this Voronoi polygons layer. I'm going to get rid of the colors by specifying outline simple line. Let's make this one a bit more thick. Alright, well, now you can see that if we are talking about rainfall data, this area of the watershed can be represented by the rainfall of this particular station, and the spatial influence of the station B is only limited to this part of the watershed, as you can see over here. And station A, D, G, E, as you can see, station E has very minor influence when we consider all of these points, and it goes without saying that the station C has the highest influence because it's sort of located in the central region of the watershed. If I look at the attributes table of this Voronoi polygons layer, you can see that the polygon itself has now been named after that particular station, which is also quite handy. Now let's say if you wanted to calculate how much of a percentage we would assign for each of these particular stations, you don't actually have to do anything manually. You can use GIS tools to actually calculate that for you. So in order to do that, first I'm going to intersect these two layers. So we can again go to the processing toolbox and search intersect. And over here under vector polygon tools, you can see there is one tool called intersect under Saga GIS tools. So I'm going to specify the layer 1 to be the Voronoi polygons layer and layer B to be the watershed boundary layer. So I'm going to intersect these two so that I can run this. And as you can see, it generates this intersected layer. Now if I were to, let's say, turn off all the other layers, yeah, you can see that now it has sort of been cut according to that particular part, which shows the contribution from each station to our area of interest. In this case, it's our watershed. You can also have a look at the attributes table. Yeah, as you can see, the polygons now has been actually splitted even though it has the same station name. Let's say, for example, if we were to look at station B, the influence of station B, you can see that even though it might not be apparent, it seems like the polygon has been split into four parts in this case, as you can see over here, a small part over here. So just to merge all of these polygons which correspond to the same station together, I can use the dissolve tool. So I'm going to go over here and type dissolve. And over here under Saga tools, you can see that there is one tool called polygon dissolve by attribute. So I'm going to click on that. And over here you can see that the layer that I would like to dissolve is this intersect layer. And if I go ahead and open up the attributes table, what I would like to do by dissolving is basically to sort of merge these different pieces of polygons which has a common name. Now for example, this polygon which corresponds to station A is actually just a single polygon, but the polygon which corresponds to station B has now been scattered actually into 4 different pieces. And I don't really need to spend time to, let's say, inspect each individual piece. All I have to do is just merge these 4 pieces together just to make it one attribute rather than having 4 different individual attributes. And similarly for station C and D, we don't have actually any splits. But for station E, you can see that the station E polygon has now been split into 6 parts. And again, I'm not going to worry too much by spending time inspect where each of these polygon piece is. I can simply use the dissolve tool to actually sort of dissolve all of these attributes into one attribute based on this particular name over here, which is under the column station. So that's what I'm going to do now. So I'm going to deselect all the selections like this. And over here, I'm going to mention that I would like to do the dissolve operation based on the name of the station. And that's it. We can run the tool and see what happens. Yeah, now you can see that over here we got a new layer called dissolved. And if I open the attributes table, now you will see that we actually just have one single attribute or one single element which corresponds to each particular station, which is actually quite clean. Now I can maybe get rid of this intersect polygon because we don't need it anymore, and maybe we can rename this to be Thiessen Polygons for the entire watershed. By the way, you can see that now one attribute has been selected. If you want to deselect everything, you can again go to attributes table and click on this one, or you just make sure that you select that particular layer and you can hit Ctrl, Shift and A, which will basically deselect any selected attributes. Alright, now in order to calculate the corresponding weight from each of these stations, you can see that by the looks, maybe I would assume that the weight from station C might be just around 45 to 50%, and from station F could be about, let's say, 25 to 28%, something like that. So that's just my estimation, but the way to mathematically calculate that would be by dividing the area of each of these polygons by the area of this entire polygon. That will actually give you the weight, but if you want to convert it into a percentage, you can just multiply that by 100. And we don't have to really do any of these manually. We can use the GIS tools of QGIS to actually do the computation. So to make things clear, what I'm going to do is I'm going to create one column over here first and calculate the area of each of these pieces. Just like this. So for that you can go to this field calculator, and I'm going to create a new field called area, and the field type I'm going to actually return it to be a decimal number with maybe 2 decimal points. And if you want to calculate the area, the expression to calculate the area of each attribute is simply a $, and after that you can type area. And this will calculate the area in square meters, but I would like to convert it into square kilometers because let's say the numbers can be too big if you were to work in square meters. So I'm going to multiply this by 10 to the power minus 6. And when I click OK, you can see that now the area was calculated, and as we can see, station C has the highest area, which is about 335 square kilometers. Well, the area of influence from station F is also quite significant, about 200 square kilometers. And the others get calculated accordingly, as you can see over here. I'm going to create another column called weight, and I'm going to divide each of these values by the total area of my watershed. And now let's see how we can do that. So I'm going to name this column as weight, and it's a decimal number, maybe with 2 decimal points. So as you can recall, what we need to do is divide this number. In this case, I'm going to specify the name of the column within quotes like this. Yeah, every time when you specify a name of column, you need to specify that inside these quotes so that it'll understand that you're actually referring to this particular column of this attributes table. And I'm going to divide that by the sum of this area column. Now if I remove this part, you can see that if I take just the sum of this particular column, you can see a preview over here. And that preview actually shows you what is the value that will get calculated if you were to just execute this one. And if you just leave it at this, it's just going to calculate the sum of all of these different pieces together, and it's going to result in a value of 686.4 square kilometers. But of course we would like to divide this each individual attribute, and that's why I'm going to divide this attribute so that for each row that you see over here, it will divide this particular value by this total area, and then it will move into the next row and it will divide this particular value by this total area, and so on. Alright, so I can simply hit OK, and now you can see that station C has a total weight of 0.49, which is 49%, which basically says that as long as you're talking about this particular area of interest and this set of rainfall stations, based on the computation of the Voronoi Polygons or Thiessen Polygons, station C will have an influence of 49% and station F will have an influence of about 29%. And as you can see over here, the lowest influence is actually from station E, which is only 1%. Now, for example, if you were to do an actual calculation, let's say that for a particular area, as you can see on the screen, we have these values which are in millimeters per year for each of these stations. And if I were to calculate the rainfall on my area of interest based on these individual stations, the way I would do the calculation is just like this. As you can see over here, we multiply the corresponding rainfall value of station A by 0.06, and we add that to the product of the total rainfall of station B multiplied by 0.05, the rainfall value of station C multiplied by 0.49, the rainfall value of station D multiplied by 0.11, station E, station F, and then we sum up everything together, which will result in this to be our total calculated rainfall over this particular area by considering the influence of all of these stations. Alright, I guess you guys got the idea. Alright, now let's move on to a bit more complex example. I'm going to save all these edits and I will turn this one off for the time being, and I'm going to turn on these sub catchments. Now let's try to do the same thing, but this time we are going to calculate the influence for each sub catchment. Alright, I'm going to follow the same workflow, which means first I'm going to create the Voronoi polygons again. And my input layer is again going to be the rainfall stations. As we can remember, the buffer we specified about 25% if I recall correctly. And it generates the Voronoi polygons for us, just like this. Now I'm going to intersect these two layers again. Well, before that I would like to inspect what kind of attributes we have in this attributes table. In the subcatchments layer we have these attributes: shape length, shape area, the name of the subcatchment, and also we have the area over here, which is again in square kilometers. Now in case if we did not have this column, you know exactly how to calculate. We can go to the field calculator, create a new column, and just specify $area, and it will actually calculate the area based on its spatial extent for each of these different attributes. In this case, the attributes are actually subcatchments. And if we inspect this Voronoi polygons layer, you can see that we basically have the area of influence specified by these different polygons, just like this. So let's go ahead and intersect. And I'm going to use this intersect tool of Saga. And my layer A is going to be the Voronoi polygons, and the layer B is going to be subcatchments. Yeah, once the tool computes the intersect polygon, I can maybe turn these two layers off. And now you can see that each polygon has been splitted accordingly. Well, if I retain this, I think it'll be a bit more clear for you guys. Yeah, just like this. Alright, now you can see that this was a single subcatchment, but based on this computation, you can see that now this single subcatchment has been splitted into three parts. If I take this identify features tool, you can see that this itself is one single subcatchment. You can see that this part of the subcatchment is influenced by station D, and this part is influenced by station A, and a majority of the subcatchment is influenced by station C. And if you were to talk about this second subcatchment, you can see that this upper part is influenced by station A, and the rest of the subcatchment is actually influenced by station C. So the contribution according to this calculation of Thiessen polygons, you can see that it's just influenced by two stations. The aerial influence of these two stations is actually sufficient enough to cover the entire subcatchment. And similarly, if you go over to this subcatchment, you can see that we still have to make use of three. For this, you can see that small piece is represented from this station over here. So it's going to be just two stations. And over here, it's just going to be station E, station F, and station C. And finally, for this subcatchment, it's going to be station F covering this majority of the subcatchment, station B covering this part, and station C is actually showing a little bit of an influence over here. I'm going to deselect everything now. Now let's have a look at this attributes table of this intersect layer. Alright, now if you double click on this name over here, you can see that it gets sorted according to the name of the subcatchment. You can see from this attributes table as well as from this graphical figure that this piece of the watershed is influenced by station C, which you can see over here as well, and this piece by station D, and this part of the watershed by station A. Similarly, you can see that if you were to select both of these parts of subcatchment 2, you can see that the entire catchment gets selected, and Similarly, you can see that this lower part is influenced by station C and this northwestern part is influenced by station A. And you can see that already we have one column called area over here. Now this area, if you see, if I check for all pieces of sub-catchment 1, the value is same. And if I check the pieces of sub-catchment 2, you can see again the value is actually the same. So where does this value come from? Well, we intersected two layers. We intersected the Voronoi Polygons layer with the sub-catchments layer. And this value is actually coming from these attributes that we had in the sub-catchments layer, which is this value. So it's quite crucial that you calculate the area before you actually proceed with the intersect operation. So now all I have to do is divide the real area of each of these pieces by this particular area. And that'll give me the corresponding weightage of each of these stations to this particular watershed, as you can see over here. So what I'm going to do is similarly, I'm going to open up the field calculator. I'm going to name this one as area of each attribute. Let's keep it in decimal numbers with 2 decimal points precision. And again, if I want to calculate the area, all I have to do is just put a $sign and type area. And that'll calculate the area, the attributes area over here. But I did a small mistake by actually not converting this into square kilometers. Well, you don't have to worry much. In case if you happen to do a mistake, you can again go back to this field calculator. And now rather than creating a new column, you can actually update an existing column, which happens to be this area of the attributes over here. And now I'm going to retype whatever I need over here. And I'm going to convert it on the spot to square kilometers by multiplying it by 10 to the power minus 6. Now you can imagine that if we are talking about, let's say, this particular watershed, if I divide this 113 by 195, it'll give me a certain weight or a certain percentage, which shows me the contribution of station C to this particular catchment, and similarly the contributions or the weight from station A and station D accordingly, if I were to actually divide this value by this value. And that's quite simple, as you can already imagine. All we have to do is go over here to the field calculator, create a new field called weight, change this to decimal number, and now I'm straight away going to divide one column by the other. So as you can imagine, all I have to do is just put the quotes like this and specify area at divided by area, just like this. And if I hit OK, you can see that now it actually calculates the corresponding contribution. Now you can do a quick check. Just simply whip up your calculator and see that all these weights, the sum of all these weights for each sub-catchment actually should be 1. So let's do a quick check. If I were to consider the sub-catchment 1, if I just add up 0.58 plus 0.04 plus 0.37, it should be, well, 0.99. We can attribute that to B1. And similarly, if I check for sub-catchment 2 over here, it's going to be 0.81 plus 0.19, which is 1. And similarly for sub-catchment 3, we can see that the 3 weights will add up to 0.76 plus 0.12 plus 0.11. Yeah, 0.99, we can attribute that to 1. So you can see that our computation is actually quite accurate. Now in the meantime, I would like to also draw your attention to some of these items which has actually a contribution of 0 over here. So you can basically ignore them. If you really don't want to have the attribute, you can even directly delete it as well. But if you were to do the actual computation, let's say we have a certain rainfall value, and you can see that the contribution for this particular piece of the polygon from station B to sub-catchment 5 is basically going to be 0. And the same case for this as well. As you can see over here, it's actually this small piece. So that's why we get a very small value. It could be something like 0.000 something. But since we specified only 2 decimals, it's actually going to show us that the contribution is just 0. So before we wrap up this tutorial, let's say if you wanted to calculate the rainfall which corresponds to sub-catchment A, the computation will be like this. You have 58% contribution from station C, 37% contribution from station D, and just 4% contribution from station A. And similarly, you can do that for each sub-catchment. Alright guys, so that's about it for this tutorial. We covered quite a bit of things, but I hope you guys got the basic idea of how we can actually utilize this Thiessen Polygons or this Voronoi Polygons tool to our advantage to easily calculate the area of influence based on a set of sample points, just like this. And again, I would like to stress the fact that this was just only an example which uses the contribution of rainfall from each of these stations to different sub-catchments, but this concept can be applied in so many different other fields. I'm going to leave the research up to you guys to do. If you do have any questions, don't forget to comment them down below. And if you did enjoy the tutorial, and if you do believe that the tutorial added some value to you guys, show your support by hitting that like button, and do consider subscribing to this channel to see more interesting tutorials like this on a weekly basis. I'll see you guys again in the next one.